Hello, everyone. This is yet another technical walkthrough call, which is a part of the educational sessions, technical walkthrough course of the Ethereum Attackathon, which is currently live on Minify. We're here joined by a gentleman from Geth project. Go Ethereum code base is fully in scope for this attackathon. And Felix and Martin are going to walk us through the functionalities and the in-scope code, and essentially what's the most valuable for them, like what findings are the most interesting for them. So, gentlemen, please take it away.
Yeah, right. So yeah, this is the Go Ethereum repository. And for this attackathon, we are specifically interested in submissions related to the areas of Go Ethereum which are under consensus. And this includes operation of the EVM, processing of blocks, just the state transition within the block, and also the validation of transactions. And apart from that, we are interested generally in submissions related to peer-to-peer networking, and this includes DOS attacks on Geth nodes or the network as a whole, and Eclipse attacks on the discovery and P2P protocols. And I guess now we will just show quickly some of the areas in the code base which are related to all of these topics. The consensus area of Go Ethereum is mostly located in the subdirectories core and consensus, with most of the logic residing in the core packages. And the core contains the EVM and the processing of blocks. And yeah, this is, I guess, where we are most interested to learn about any vulnerabilities and potential issues.
If I can, can jump in a little bit. So the EVM, I mean, everyone probably knows what the EVM is, but when we execute within a contract, that's when we invoke the EVM, and that's where we have these operations like add or sub or mul or whatever. And that's a highly important part of Go Ethereum, which needs to function identically to all other nodes. Otherwise, we'll have these consensus issues. Whereas with the state processor and state progressions, it doesn't concern the EVM directly, but it's rather about validating how the block is constructed and whether the block is valid at all or not. And that can also lead to consensus failures where the chains start diverging. And the main part of the EVM is in the VM or the interpreter. I keep mixing those up.
Oh, you mean when you're actually talking about the EVM?
Yeah, so the EVM and the implementation of what actually happens under the hood when a contract executes.
Yeah, right. So I guess the main entry point is in the EVM itself. So there is this EVM object that represents the virtual machine itself. And this then, all of the transactions, they will ultimately hit either this function call, which is invoked for a transaction that performs a contract call, or it will be invoking the create function, which is for create transactions with no destination contract. And basically, it's this operation here, EVM create, and it will first create a contract and then run the in the context of that. So yeah, these are the two main entry points into the EVM.
Yeah, and the main run loop of the EVM is located in the interpreter.
Yeah. So that is then, that then goes into the interpreter.
And that's kind of interesting just to peruse. It's actually very readable and easy to understand. Little run loop where we patch operations and then execute them.
Yeah. Yeah, that's correct. So I mean, we have the run loop, but it's not likely that there will be any issues specifically in this loop. It will more like be within the context of operations or in the context of operations interacting. But this basic loop, yeah, I mean, only like 100 lines or so. I don't think there will be anything here. But yeah, I mean, this is basically where it actually happens. So yeah, kind of interesting in itself. I kind of wanted to zoom out a little bit and go like, basically now we're kind of going from the inside out. It's pretty interesting, but I think it's also good. So the EVM itself is actually invoked by the state processor, and the state processor object in package core. So you can kind of see it here, like we're now in package core and the file state processor Go, and it has this function process is basically the main state transition for the whole block. So this is basically where we process an entire block. And we process the block on top of the state. Sorry, and now I kind of jumped away there. Basically, here what we kind of do is just at a very high level, we have these like pre-execution operations that happen before any of the transactions go. Then we have the actual transactions where we apply each transaction to the state. And then we finally have some post-processing that we do. All of this is actually kind of new for the next fork. It's not really something that is even active right now. You can see a lot of times in the code base, operations will be gated by the fork. So it's kind of this case here as well. Like this whole block will only execute when the prog fork is active. The prog fork isn't even scheduled to occur yet. So this code is basically not active right now. And then at the very end, we sort of finalize the block by just, applying any kind of, final computations on it. But this doesn't typically involve the EVM, and we're kind of done. So basically, the whole thing is just that block processing is in the big part just processing transactions, and everything will sort of happen in here. And then within the context of applying transactions specifically, there's just a lot of things that ultimately will, where is it actually defined? I'm pretty sure it should, isn't it in this file? Have we moved it? No, it's here. Oh, no.
Apply transaction with EVM.
Yeah, applying. So in the context of processing a block, we have this concept of applying a message. So message is typically a transaction, but it can also be a non-transaction. But basically, a message is just an internal representation of a transaction. It's kind of the same thing, it's just called a bit different way. And this, like applying a message, this is the actual Ethereum state transition as it is defined in yellow paper as well. So basically, this is where like a single transaction is applied, and this happens within the state transition of Go. So yeah, and this is also where a lot of the logic related to, for example, gas and forks is located. Like as you can see it here, for example, there's a lot of these cases where like code is conditional on some fork, or it has certain rules that are only active at some point, and like this is kind of where all of that is. Anyway, so just moving out a little bit. I mean, I guess this is actually like these two files are basically the main files. It's like state transition and state processor. This is where the actual sort of like block processing happens. We also have a lot of other logic in here that might be interesting, but honestly, yeah, I mean, if a bug is found in these things and it can ultimately have a bad impact, then obviously it would be considered for a reward. But I kind of guess most bugs you could find would more be classified as bugs and not so much vulnerabilities, whereas when it goes to the state processor, state transition is very likely going to be a vulnerability in the end, because all of that code really happens under consensus.
One thing that's worth mentioning, it's a mistake that I made back in like 2016, and also a mistake that happened last week. It's not really a mistake, but something that's easy to do is to find a consensus error which hinges on being able to use massive amounts of gas. So I'm sure you could find a case where, if you have a couple of billion gas, you could do something which causes an overflow, and therefore a consensus issue. And we don't actually care about that, because if we have billions of gas, you could always make an allocation of memory in the petabytes or whatever and crash the node.
That's correct.
Geth, we're just simply not able to operate under conditions where you approach above the UN64 level of gas. So that's, for example, one assumption we've made. You can never have more than UN64 max gas.
So that's kind of the thing. For example, here with the memory, like Martin just mentioned, operations in the EVM which require memory, they are metered according to the gas, obviously, but it also means that you would actually have to pay for all this memory, and the cost kind of becomes sort of quadratic in that. So it kind of means you would basically not be able to pay this amount of gas. So, I mean, if there's a fundamental issue with the gas calculation, of course, or the accounting of it, then maybe you would be able to, but then this would also lead to other issues. So we received quite a few submissions where people actually find bugs that ultimately end up not being exploitable because it would require a lot of gas. So it's good to mention that. Should we maybe move a bit out of there? So you also mentioned, Martin, that you wanted to consider a transaction validation to be in scope, or maybe should we now show it like the EVM tool?
Yes, showing the EVM tool sounds like a good idea. So the EVM, it's possible to build the EVM as a standalone binary. And I know that other client implementations have done the same. Using this binary, you can either just run some code and see the output in a human readable or JSON form, or you can execute more formalized state test where you can define the full pre-state and more complex allocation. But Felix showed just the code run there.
So here, Martin has prepared a little example for me to show you guys. So basically, this is just an invocation of the EVM binary with some bytecode. In this case, it's like pushes two values, I guess. So this is like
a push 140, push 160.
Right. So if we run this, and we also have the JSON flag. The flag handling in the EVM tool is a bit weird. So basically, you have to put the flags and then the operation at the end. So this run is basically the operation that we're running. It's like run the EVM, but you have to put the code before. And here you have the JSON output. So this means that when we run this, we will get a JSON log for every step of the execution. So you can see the operation that was executed is push 1. And then we have...
the next line, you can see that the stack contains...
The stack contains 0x40. So it's like contains this value that was just pushed by the push 1. And then here, this line is actually another push 1 operation. So on the stack here, you can see that now we actually have the 60 on the top. So the top is actually the end of the stack. And that's that. And then the final operation is stop. This operation is actually not in the code itself. It's just sort of every execution ends with stop. So that's that. Like implicitly, the EVM, when it hits the end of the bytecode, it will hit the stop operation, which is opcode 0.
I think we're the only client that does that. The others omitted.
Interesting. Anyway, so also on the very last line, it will show the total amount of gas used. And actually, this can be configured as well. So if you have, for example, you can actually go to the use, for example, the gas flag. So here, if we use this flag gas to put like 2000 gas, then it will work. But if I put like 1 gas, then it will run out of gas, like on the first push instruction. So that's that. Anyways, so this is it about the EVM. You also mentioned that, Martin, that you would be interested in submissions related to the transaction validation. Can you go a bit more into the detail of that? Like, where would that be? What kind of area?
So, I mean, originally there was only one transaction, which in that one is currently called a legacy transaction.
Right.
Since
types.
Since then, throughout the years, we've accumulated some, and we're about to add another one soon in the next fork. And
Yeah, that's true.
yeah.
We have actually within Ethereum there's this concept of transaction types, and the transaction types in Go Ethereum, they're represented by these objects, but then ultimately all transactions, they become this, like they are all hidden in behind this kind of like wrapper object. It's just called the types of transaction. So it's here, and it does contain inside like various transaction types, but like there at the moment we have, I think, 4 different transaction types. So we have legacy transactions. First of all, these are like the original ones. We have the dynamic fee transaction, EIP 1559, which added this like gas fee cap, gas tip cap fields. Then we have the access list transaction, which contains the access list. Notably, all other transactions introduced after access list TX also contain an access list. So this transaction type now is a bit redundant because this was defined before the EIP 1559. So now in 1559, we also have an access list here. So you don't really need to use this transaction. Like this transaction type is not commonly used. And then now also we have the blob transactions, which are also contain an access list, and they can contain blobs. So there are various differences between these transaction types. Maybe Martin, you can go into the detail of it.
Yes, actually not going. I wasn't planning on going into the difference between transaction types. I was more interested in telling what would be typical errors that we can expect here.
Yeah.
So that on the network, these are on a form which is called RLP.
Yeah.
And then they are passed around and they are parsed by clients. And at the end, when they're included in a block, they are hashed, and the combined hash goes into the transaction root. It's called the transaction root and goes into the block. And if the clients disagree about the hash of a certain transaction, then we can wind up in large problems. And this has happened in the past in some cases when there is an ambiguity. In RLP, there's typically one ambiguity regarding empty lists and the value null. There's something about that, which kind of can be encoded in 2 ways. And it is one thing that we have actually done a lot of fuzzing on is seeing how does a client interpret this blob of bytes. Can it be parsed as a transaction or can it not? And differences in those areas, blobs of data which can or cannot be accepted as transactions, that is interesting because it could cause various forms of headaches, possibly consensus issues. If someone manages to include a bit of data in a blob, which another client considers, no, this is not the canonical representation of a transaction.
No. Yeah, that's correct. So like I kind of want to mention here on the side that we actually do include some built-in fuzz tests as well. Like they are a part of the repository as well. Like these are the fuzz tests that we pretty regularly run. So for example, here, like within the tests subdirectory, we have all of these sort of official tests for Ethereum. Like we get these from the Ethereum. It's called the Ethereum test repository, but nowadays also from the execution spec test repository. So there's a bunch of repositories containing like ready-made test cases that we also use. But then we also have our own fuzzers here. These are using the Golang fuzzer fuzzing functionality. And didn't we have some for the encoding of transactions and so on, or have they been removed? Or we used to have like an
I'm not sure. I know that we have some RLP fuzzing parsing. However, the most interesting thing is to use differential fuzzing with transaction parsing against other clients.
Okay. Is that here or?
No.
No. Okay. So we don't have that in the repo. Okay. All right. Then let's just skip over this. I wasn't really sure. I kind of vaguely remember that we actually had some like fuzzing for transactions, decoding and stuff, but maybe it's not in here anyway. So yeah, so this is a bit about the transaction validation. One very big area of interest for security researchers traditionally also is the mempool, or the transaction pool as we call it. And this is located in the package core/tx pool. And then actually the implementation of the transaction pool for regular transactions that can be sent on Ethereum is located in the legacy pool directory, because internally we actually have two different transaction pools, one for all transactions, and then one which is specific for the blob transactions. And this is called the blob pool, and it has very different rules compared to the legacy pool.
I would though mention that we do not, I mean, it is possible to do shenanigans against an individual victim's transaction pool.
Yeah.
And we kind of accept that. It's not a perfect pool, and it's not a consensus structure.
Yeah.
So if an attacker can send a lot of crap and the user or victim temporarily winds up with a somewhat crappy transaction pool, it's not the end of the world. So yeah, I would rather attackers focus on other areas.
Yeah, that's true. So definitely attacks against an individual transaction pool instance are kind of also a known area, and there are a lot of known issues in there that we kind of consider acceptable. It's mostly just there, if an attack can be found that significantly impacts the entire network, then it will be a problem. But it's something to consider as well that the transaction pool implementation is like fully left to the implementations of Ethereum. So within Go Ethereum, we have one implementation of the transaction pool, but other Ethereum execution layer clients may have very different transaction pools. And this means that typically an attack will not translate across the clients. So yeah, it's always something to consider, is that these, even if an attack can be found against a specific node, yeah, it's interesting, but it's not as interesting as like finding an attack that can cause a network-wide issue. And typically they do not just attacking a single pool does not typically affect the whole network. Yeah, so that's that with the TX pool, and maybe it's a good segue into the whole P2P area. So we also have this subdirectory ETH, and this contains sort of the like Ethereum node implementation. So the core is only related with processing blocks and transactions and so on, and implementing some of the very critical data structures and algorithms related to Ethereum. But the ETH subdirectory contains all of this like node functionality. So this includes P2P networking protocols on the high level, syncing the chain, and then also the engine API. So nowadays, the Ethereum is split into the execution layer and the consensus layer. Go Ethereum is an execution layer node. So it receives communication from the consensus layer over what's called the engine API. And the engine API is basically a JSON RPC API provided by the execution layer, which the consensus layer will submit blocks to as they become agreed upon by the consensus. And it will also make various requests to this API to, for example, build new blocks. And the implementation of this API is located in this file, eth/catalyst/api.go. And yeah, we are also interested in finding vulnerabilities related to wrong processing of such requests. However, this API, since it is a privileged endpoint, it will never be exposed to the internet. So basic vulnerabilities on this API in terms of, like bad RPC payloads or any kind of whatever, like web-based attacks, they do not apply to this API because it is an internal API used for communicating between two trusted pieces of software. However, it is still very interesting to find vulnerabilities related to incorrect processing on this API, because it can lead to some issues. And maybe just fundamentally how RPC APIs in Go Ethereum work, because this is basically like any other one that we have. This object here is the consensus API object, this implements the API methods, and any public Go methods on that object will be callable via RPC. So you can see it here, this function, fork choice updated v1. This will, in fact, be callable over RPC. So if a caller submits a JSON RPC request containing the method name engine underscore and then lowercase fork choice updated v1, then it will hit this method in the end. And the parameters of this method will be decoded into by the RPC layer, and basically they will be submitted then here to this call. So in the engine API, we have version methods. So there's also fork choice updated v2, fork choice updated v3, and so on. And these typically only the latest version is used by the consensus layer. So these old methods, they are mostly around for compatibility with old forks, but ultimately they will become disused over time. So mostly we are interested in the latest version of each of these methods. So we have fork choice updated, but there is also, for example, get payload and new payload. So these are basically the core operations of the engine API is fork choice updated and new payload. So these are the ones that basically can cause the most damage in a way.
While we're on this, since you mentioned the RPCs a bit, generally we consider the RPCs to be privileged surface, and any user who we discourage users from exposing the Geth RPC against an untrusted environment such as the internet. And we're not really surprised if someone from the internet is able to crash a node over RPC if they have access to it. So we're not super. It's not something we're really interested in. But yes, we try to harden if we find something horrendous. But it's not really an area that we feel is very interesting for attackers, for vulnerability researchers to dig. And we don't pay high reward, so we don't rate it highly if it's an RPC attack.
Yeah, you mean against like basically user-facing APIs, right?
Yes, I mean like
So this
debug or ETH.
Yeah, but this is not that. So the Catalyst in ETH Catalyst, we have the engine API. We also have another user-facing RPC API, but I'm not showing that here. So basically, it's kind of out of scope basically for bounties, anyways. But then within the ETH package, we also have, for example, the downloader, and we have this protocols thing. So this is basically where the ETH wire protocol is implemented. So this is the peer-to-peer wire protocol. And
just to clarify a bit, so Ethereum has one protocol called ETH, currently on ETH 68, right?
Yeah.
Which concerns how we pass blocks and transactions and things between nodes in the network. There's another protocol called Snap, which is used when we do the SnapSyncing, and it relates to sending parts of the state. So one node can query another node and ask that node to give him, for example, 5,000 accounts from the trial. Those are the main high-level protocols, right?
Yeah, that's true.
Apart from that, there's a discovery protocol, and then there
we'll
RPX on the you'll get that.
So basically, one thing to keep in mind is that the way the structure is the way the code is structured here is that within the ETH subpackage we have this protocols directory, and in there we have directories for each protocol. Here we have the Snap protocol, and in handler.go here we have function handle message, which is sort of the main message handler for peer-to-peer messages coming from a particular peer on this protocol. So here, for example, you can see we are here switching on the message code, which is just a type of command sent by the other peer. And here, for example, we have this get account range message. So it's like the peer is requesting a range of accounts to be sent, and this is where we actually ultimately handle it. So here, for example, we get the accounts that they requested, and then we use this operation P2P send to dispatch the answer to this peer. So this is just how this is basically how they all work. And we have the same for the ETH protocol as well. So for example, here in the handler, we probably also have the handle message function. Yeah, I'm wondering, actually, we have handle here, which sort of is a loop that handles the messages. But I guess, yeah, we kind of have the same function. And here it actually works a bit different. We have a map-based approach where the individual handlers are defined as functions which are located in the map. So here, for example, we can have operations such as handle get block headers, for example. So here, yeah, we receive this message get block headers. It has a certain structure. We decode the message, and then we do kind of same as in the snap. Basically, we try to come up with the answer, and then we respond to the peer. So, but on a more fundamental note, we actually have kind of this higher level structure here in the ETH protocol, where basically the ETH protocol is used for syncing the chain. So when the node starts and the consensus layer requests a block from it that is not known to the execution layer, then it will start the sync, and the sync process is handled by the downloader, which is a kind of a complex piece of code. I'm not really gonna go too much into the details there, but we are actually very interested also to learn about vulnerabilities in that area. Another aspect of the ETH protocol is the transaction relay. So this is sort of the networking part of the transaction pool, and this functionality is located in the ETH/fetcher directory. So here we have the fetcher object, which contains sort of all of the in-progress transactions that are being relayed among the peers. And yeah, I mean, basically all of these public methods, they will ultimately be called by some part in the system, either from the transaction pool or from within the peer-to-peer message handling. So yeah, this is like another very interesting area. And then finally, we also have the low-level peer-to-peer networking. This is located in the P2P directory. So, and here we have the peer discovery protocol in P2P discover. And we have the basic peer-to-peer protocol that is used in P2P RLPX. We are not interested in learning about vulnerabilities in RLPX unless they are sort of like DOS vulnerabilities. But when it comes to, for example, the cryptography used in RPX, it is explicitly out of scope because we know it is broken. Yeah, in general, we are interested in like interesting attacks related to peer handling mechanics. So this is something worth knowing. But yeah, I guess it's kind of hard to point to a specific area in the code that could be interesting for that. It's just more like you just have to explore the implementation here and then see for yourself what's there. Yeah, and then yeah, I guess this kind of concludes our overview. Or Martin, do you have some other?
No.
Yeah.
Well, one thing though maybe worth mentioning, if you're interested in the networking stuff and the discovery stuff, there's a repository which contains the protocol definition. And Felix, you maintain that, right?
Yeah, so I'm the maintainer of that. So it's this repository, the Ethereum Dev P2P. This contains the networking specifications. At the same time, so for example, here in the CAPS directory, we have the ETH protocol specification that explains some stuff and shows the messages and the encoding and so on. And similar for the Snap. Yeah, however, I mean, the specification is interesting just to learn more about the protocols, but I guess it's not like in terms of vulnerabilities, this is not really what we're here to talk about. So yeah. But it might still be interesting just to learn a bit about like how it actually works and have a bit of text explaining what the protocol is all about.
Other than that, I think we're yeah, I don't have anything more. Yeah, sorry, one more thing. Yeah, one thing that I had written up before. I don't know if you mentioned this, but generally we are not interested in denial of service attacks which rely on the attacker just having a big bit pipe and is able to shoot a lot of traffic at an individual victim.
Those are out of scope, Martin. Don't worry.
Okay.
Yep, those are out of scope by default. Wonderful. There are actually a bunch of attacks out of scope for those who are watching. You can check them out in the out of scope section, and those are like denial of service, DDoS attacks, privileged access attacks, and all that kind of stuff. All right, Felix, Martin, anything else that you want to cover?
No, I guess not.
Wonderful. Then I think we can conclude here. Yeah, thank you everyone who was watching. I think this was a wonderful session, and good luck on the hunt. Good luck with the Ethereum Attackathon.
Yeah.